So let's kind of take a minute and put some of this into use. So let's look at a video real quick. So let's look at this one. So let's see how this goes. All right. So this is a situation. This video is pretty old now, but right, really famous runner, Usain Bolt, the guy in the yellow who set a new world record. Woo! So there's lots of quantities going on within this situation, right? So even if we just watch the video, we don't even have to watch the race. We could just kind of pay attention to what's going on in the video, right? So one quantity I could think about is I could think about how many racers there are. So that is something on the track. How many racers there are, how many laps, how many like curved lines, how many dotted lines, how many advertisements, right? How many people standing on the track because there's that guy in the white who's not just he's not a racer, but he's there. How many cameras, right? So those are all things as we race. Now we can start to think about some other things. Sorry, I know that's really awkward, but I don't want the noise right now. Um, right? We could talk about the distance between two of the runners. We could talk about Usain Bolt's speed. We could talk about the speed of the second runner, the speed of the third runner. We could talk about their stride length. We could talk about how long it takes each of them to finish the race. These are all different quantities, different things that are happening. And we could talk about measuring each one of those. So those are lots of quantities. Oh my gosh, I'm so overwhelmed by that. So let's slow down and let's look at just a couple of them. So let's look, we'll focus on the guy in front. So Usain Bolt. And about him, we are going to look at the distance traveled since the race started. And we're only going to worry about it until the end of the race. I know he kind of keeps running around. I'm only going to worry about that part. And then let's look at the time elapsed since the race started or since the gun went off, however you want to say it. Since race started, I'll be consistent. So let's kind of take a look. So we'll watch it again. Focus on those two things. So let's just go back. Let me restart it. Here we go. All right. So what I want us to do next is think about how we could graph the relationship between these two quantities. So just take a second, pause, and think about that. Maybe the first question we should ask ourselves is if we're drawing a graph, there's really two different ways that we could, ooh, my lines are different, oh well, that we could label it. So one way is that I could put the time elapsed here. And I could put like Usain's distance from the start here, right? Like that's one option. The other option is we could just flip it around. So Usain's distance from start and the time elapsed. So in this situation, I just asked us to graph the relationship between them. So if in terms of saying like which one's right and which one's wrong, the answer is neither, because either way we label our axes, that's going to show the relationship between the two quantities. Now, we might ask ourselves, like, is one going to be what we desire more than the other one? Will the graph change based on the way we draw the graph? So those are some things that we should consider. But there are a few ways several ways we really could draw the graph. So like maybe let's start, I guess I'll start with the graph on the right. So maybe we could start by thinking about something like this. If we drew the graph this way, that is communicating something about how time elapsed and Usain's distance from the start changed together, right? So we could be saying, so this would be saying something like, hey, as time elapsed is increasing, Usain's distance from the start is also increasing. But this isn't the only way to draw it. I could draw it like this, I could draw it like this, or I could draw a straight line, or I could do, some combination of them. But when we draw a straight line, we are communicating something very specific about how they are changing together. And so maybe the way to think about it would be to do something like this. I'll just pick some different colors. Yay, fun. Right? So we could kind of think about breaking this up like this. So if each of these, like let's say this represented seconds. So if each of these represented a second that has elapsed, really what we might be saying in this situation is, like, in that first second, he covers this much distance. And then in the next second, he covers this much distance. So this right here is a change in distance. This is a change in distance, right? In the next second, he covers this much distance. But really, if we're thinking about it, this should be the same as this, should be the same as this. When we draw a straight line, we are stating, like we are saying something. We're not just being like, I'm drawing a straight line. We are saying that this relationship between the change in distance and the change in time is always the same. So for every second, he is covering the same amount of distance. So that would be a different way of saying it. So every second, Usain travels the same distance or same amount of distance. And so if I draw a straight line, we are saying that that relationship is proportional. We are saying that that ratio of the change in distance to the change in time is always going to be the same. And that may or may not be true, but that's what we're stating. Now, in this situation, if we think logically, like, right, if you've ever challenged a friend to a race or you've watched anybody race, right, if you're starting from a speed of 0, and then at some point someone says, go. And what happens? Immediately you speed up. So really there's no way that in this, like in Usain Bolt's situation, that he's traveling the same speed the whole time, right? Because this, right, another word we can think about this right here is speed or rate of change. So really we know he has to be starting from a speed of 0, and then again, in our layman's terms, we'd say he's speeding up, right? So as time is increasing, at least for the first part of the race, Usain's speed is increasing. So if his speed is increasing, let's see if I can erase all this stuff without erasing things I don't want to erase. Right? If his speed is increasing, maybe I'll undo that. Then we wouldn't say that that is always the same, right? This is always getting bigger. So it's always increasing. And so we wouldn't say here every second you change travels the same distance. We would say, oops, oh no. Can I get there? Yay. We could say every second Usain travels I'm not going to have space, a larger amount of distance, right? Because if he's speeding up, the only way we can talk about speeding up is if we were to, again, looking at this. So this is speed. That means that this has to be getting bigger. So if this stays the same, like every second, so if my denominator stays the same, then this has to be getting bigger. So maybe in that first second, he covers some amount of distance, right? So like this part right here. But then in that next second, he needs to cover a larger amount of distance, right? So right here. And then in the next second, maybe then he covers a larger amount of distance, right? And then maybe at some point he kind of like reaches his max speed and he stays at that constant speed for a while. But in terms of our graph, we should be getting something that's curving up, at least to start. And then maybe we're like, okay, he flattens out for a while because he hits that max speed and he stays there. So for that part of the graph, every second he is covering the same amount of distance. And then from there, we could have conversations about, does he go finish out at the same speed? Does he slow down? Does he keep speeding up? Like that kind of thing. But right in this part right here, really we'd be saying he's speeding up. And so the way we could justify why we draw the graph the way we do is because we can say, hey, every second his amount of distance covered is getting larger and larger, right? Which again means speeding up. Because really what we're doing is we're breaking our speed up into its two different pieces. Because that's really what's going on. I mean, really speed is just looking at a ratio of two different quantities. All right. Now you could have the third option, which I doubt is happening, right? You doubt is happening, where we could say he's slowing down. We could still break that up in the same kind of thing. We could say like, hey, every second, ooh, my seconds aren't quite even, right? Every second in this situation, at first he covers a large amount of distance, but then in the next second, he covers a smaller amount of distance, and then a smaller amount, and then a smaller amount. So every second here, so in this situation, we would have said every second he travels a smaller distance, right? And so that would mean slowing down because this ratio is decreasing. This is staying the same, but this is getting smaller. All right, so I think we feel pretty good about this one. Hopefully you do at this point. But this is if we draw the graph this way. What happens if we draw the graph this way instead? So in this situation, and this is actually more true to life for racers, what racers or swimmers talk about is they talk about splits. So they, instead of keeping the time consistent, they do something like they keep their distance consistent. So they might say something like, hey, every 10 meters, how fast are you going? So maybe if we think of it that way, so in that first 10 meters of the race, right? Usain's just getting off the blocks. How long is it going to take him to cover that first 10 meters? Maybe that first 10 meters takes him quite a bit of time, right? But then that next 10 meters isn't going to be quite so long, right? He's speeding up. So that next 10 meters should take a smaller amount of time. And then the next 10 meters, he's really flying. So in that next 10 meters, it's only going to take him like this much time, right? And so on. And so really, if we're talking speeding up on this graph, it's going to look something more like that. Because every 10 meters, it takes smaller amounts of time, right? And that's probably not the best English grammatical way to say it, but that's kind of what we're saying here. And so actually a graph that looks like this could also mean speeding up because we've switched the axes. So a lot of times we default to being like, oh, hey, speeding up means this. But you have to be careful because the way you label the axes is actually going to change what speeding up might mean. Because even if we draw it like this, we're still really thinking about speeding up like this. This is the way we tend to process it. And so in this case, Usain, right, speeding up would mean that every 10 meters, it takes him smaller and smaller amounts of time. So really, if I were to ask you this question, or your teacher were to ask you this question, like on a test or a quiz or anything, really both of these graphs would be correct. It's just that you really do need to pay attention to the way that you label the axes. It's going to change the way that you think about it. And so just, yeah, I guess I'll stop there. This video is long enough. And if you want to keep listening, I'm sure I'll make the next one.